Hello, we're Group 69, and this is our project, Bird-noculars, bird identification with image classification. As the title suggests, our project is primarily concerned with bird identification, which is an important task in fields such as ecological research and wildlife management. Classifying birds by eye is tedious and difficult, so we're constructing a convolutional neural network to do this for us. The input of our dataset are images of birds from the Caltech UCSD Birds 22011 dataset. This dataset has 200 different species of birds with about 59 images per species. These images vary in dimension and resolution, so we have to uniformly crop and resize them during pre-processing. The output of our model are the prediction of what class of bird it thinks each image is. And here you can see our exploratory data analysis for the data set. You can see that no species of bird has more than 60 images. However, there are some with less. There are 5 species with less than 50, and the least represented is the least auklet with 41 images. On the right, you can see the distribution of the image aspect ratios. You can see that the average image is about 467 by 386. One of the challenges we faced with this task was that it is an example of a fine-grained image analysis task. This is a task where the classes have overlapping visual features between them. So in this instance, multiple species of birds might have the same bill shape, wing shape, tail shape, etc., and only differ in a few visual features.
Other challenges we faced with our dataset was the quality and consistency of our dataset. The picture may be blurry, the full bird may not be in frame, or there's visual noise that obstructs the bird. On the next slide, we'll see a couple of examples. On the left, we can see birds out of focus, not in frame, multiple subjects, or things obstructing the bird. On the far right, we can see even within the same species, birds can look quite different at different stages in their lives. As we were working on this project, we tried using several base models for transfer learning, using ResNet and EfficientNet models B1 and B2. We also tried to build a feature extraction model using faster RCNN with little success. During testing, we found the full dataset with 200 classes using all 11.5 thousand images to be both time and computationally expensive. To speed up training times, we used 150 class subsets of the data so we could get results and try to improve upon the models. Our data came with a recommended 50-50 split, labeling each image as a training or testing image. For more robust training, we also used a classic 80-20 split. As our images are divided evenly across our image classes, we decided accuracy was a good metric for evaluating our models.
Now, moving on to the architecture, we basically tried to implement transfer learning and used ResNet 18 as our base model. There are two main reasons why we used ResNet 18. The first reason being that it is pre-trained on the ImageNet dataset, which has 1.2 million images, and it can classify these images into 1,000 classes. So basically, all the hyperparameters of ResNet 18 models are already tuned, and it is amazing for image classification tasks. The second reason why we chose ResNet 18 is it because it solves the problem of the vanishing gradients, and this leads to faster training time. We made use of batch normalization, which divides huge data set into smaller chunks. So again, that can speed up training. We use the ReLU activation function. Now, ResNet, like giving you a little bit more highlight about ResNet 18, it's a pre-trained convolutional neural network model that has like 18 layers. As mentioned, it is trained on like 1.2 million images. And moving on, so basically we came up with three models, okay? The first model was trained on 50 classes, and that was again a ResNet 18 model. However, for this model, we implemented few image transformation processes, and we came up with and the testing accuracy ended up being 70.34. For our second model, we took more number of classes, and this time we trained it on EfficientNet B1, and the testing accuracy ended up being 54.47. For our third model, it is kind of based on our model 1. However, it is more simplified because we got rid of all the image transformation. And instead of the suggested 50-50 data test, 50-50 train test split by our data set, we ended up implementing the more general 80% training and 20% testing split. And this time we incorporated all the 200 classes and we ended up with a testing accuracy of 51.56%. None of our team members have done prior work with related to image classification. And on the next slide, you'll see like a couple of references. And that's it. Thank you from our side.